Welcome to this presentation on using resources via SLURM from the U.S. National Science Foundation. My name's Joel Adams. Let's see one way to use an Access resource. For the purposes of this presentation, a resource is a computing system that's part of the U.S. National Science Foundation's National Cyber Infrastructure. To use an Access resource, you must have an active Access allocation, have exchanged some of your allocation's credits for time and/or storage on the resource, and be able to log into that resource. If any of this sounds unfamiliar, I encourage you to watch the previous presentations in this playlist. When you successfully exchange Access credits for time on a resource, the follow-up emails from that resource provider, or RP, will provide instructions on how to log into their resource. Many Access RPs require you to set up SSH keys to use their resource. Exactly how to do this varies from one RP to another. The instructions you receive from the RP should include information about how they want you to do this. The rest of this presentation assumes you have followed your RP's instructions and set up your SSH keys. If you run into problems doing so, I encourage you to watch our SSH playlist that's available from the Video Learning Center on the support site. If that playlist does not resolve your problem, submit a help ticket to your RP. They can help you resolve it. Let's see one way to use an Access resource. I'm going to start by running a program called CircuitSat on Purdue's Anvil cluster. This program finds all the integer inputs that solve this 32-bit digital circuit, the inputs that make the circuit output the value 1. When I received my allocation on Anvil, Purdue emailed a link to their Anvil user guide, which includes a page on setting up my SSH key. I followed their directions. At the end, it had me test my setup using my MacBook's terminal application and entering what you see on the screen here: SSH x-joeladams@anvil.rcac.purdue.edu. x-joeladams is my username on Anvil. When I enter this, SSH connects me to a login node on Anvil. Note that x-joeladams is my username on Anvil, not my Access username. Like most Access resources, Anvil uses the Linux operating system, which offers a command line interface. When I log in, Anvil displays a lengthy message followed by this prompt. The prompt consists of my username, the @ symbol, and login07.anvil is the name of the login node on Anvil where it logged me in. We'll see what the rest of this means in just a moment. This whole thing is called the command line prompt. It lets me interact with Anvil by entering commands using my keyboard. For example, I can use the ls command to list the contents of my current folder, which Linux calls a directory. We'll use both terms, folder and directory, interchangeably. Entering ls by itself reveals the contents of my current folder, my home directory, which contains two folders, one named Examples and the other On Demand. If I enter ls followed by Examples, ls's response indicates that my Examples folder contains two folders named CircuitSat and GenScan. I can then enter ls Examples CircuitSat to view the contents of my CircuitSat folder. Based on your terminal settings, Linux may use color coding to name files and folders. Here, normal files are shown in black, program files are green, and folders are blue. So my CircuitSat folder contains 3 normal files: 1x1-slurmscript.sh, 2x64-slurmscript.sh, and slurm-15857.911.out. One program file, CircuitSat, and one folder, SRC, which contains the source code for the CircuitSat program. Linux tracks your location within its file system, which it calls your working directory. At the moment, my working directory is my home directory. I can change that using the cd command. And by cding to examples/circuitsat, note a couple of things. What was this little squiggle or tilde symbol in my prompt changes to circuitsat. The thing that is between the square brackets is the name of my current directory. If I enter ls again, I can see now that I am in my circuitsat folder because I get the same thing as I got previously. If I enter cd with no arguments, note that my prompt changes from circuitsat back to tilde. Tilde is an abbreviation for my home directory. And I can use the up arrow key several times to go back to that cd command and enter it, and now I'm back in circuitsat again. Without further ado, let's see how we can run this program. An access system may be shared by thousands of users. To ensure equitable access and usage, most access resources use a scheduling system called the Simple Linux Utility for Resource Management, or SLURM. The files 1x1 slurmscript.sh and 2x64-slurmscript.sh are called SLURM batch scripts, files that tell SLURM how I want to run my program. You can name these files anything you want. I like to give them names that describe what they ask SLURM to do. I can view the first file using the cat command. When I enter that, here's the command I entered, and everything from that point on is the contents of the file. A SLURM script consists of a series of sbatch directives, followed by the command to run my program. The directives in this first script tell SLURM to run the circuitsat program using one node, one task or process per node, for a total of 1 tasks. In other words, to run it like a traditional sequential program. It also tells me the Anvil partition on which to run it, my allocation to charge for this, a maximum time, a job name for it, how we want to view our output, and some email directives. A detailed explanation of these directives is beyond the scope of this presentation. For a deeper dive into SLURM, I encourage you to watch the Access playlist, Getting Started with SLURM, that's available in the Access Video Learning Center. CircuitSat is a C program that uses the message passing interface. So the end of the script tells my program to use MPI run, how many processes to use. This variable will be 1 since the number of SLURM tasks up here was 1, the name of the program to run, and that's it. I can submit this script to SLURM using the sbatch command. When I do this, SLURM puts my request in a queue, assigns it a job number, and displays that number. If I copy that number, I can check its status using the sq command and the -j switch. J stands for job. The output here indicates the job, the user, the account, the name of the program, how many nodes and CPUs or cores were requested, the time limit, and its status. PD stands for pending. Using just one core, this CircuitSat program will run for over 4 minutes, which is wasteful. I can stop it using the scancel command and my job number. If I then repeat my sq command, I can see that the queue is now empty. My job is no longer there. If I run ls again, The file slurm-158579111.out contains the output produced by my CircuitSat program during a previous run of the 1x1 slurm script.sh. I can use the cat program to view that output. If I scroll up, the program starts saying it's checking the circuit using 1PE, and there's a column of the binary inputs that satisfy the circuit, another column of their base 10 equivalents. And if we scroll to the bottom, at the end it says 1PE found 81 solutions, and it took about 243.5 seconds, so over 4 minutes. The program uses a brute force algorithm that tries all 2 to the 32 possible inputs to the circuit. So out of the 4.3 billion integers it tried, just 81 of those were solutions. What was the name of the other SLURM script? Let's use ls again. If I cat 2x64, I see that it requests 2 nodes and 64 tasks per node for a total of 128 tasks. As an MPI program, CircuitSat will distribute the work of trying all 2 to the 32 possible inputs across the available PEs. So 128 PEs, it should finish much faster. To run CircuitSat using this script, I will again use sbatch. But now I specify 2x64. And here's my job number. I can again use SQ to check it. I could use -J in the job number, but for variety, I could also use -U followed by my username. If I have submitted multiple job requests, this approach will list all of them for me. Again, the PD in the output from SQ indicates that my job is pending. Since I'm requesting more nodes and cores, it may take SLURM longer to launch my program, because 2 nodes with 64 cores must be available. But once SLURM launches it, CircuitSat should finish much faster. On a busy shared system, the more resources we request, the longer it is likely to take for those resources to become available. This is an incentive to only request the resources we actually need. If we use the up arrow again and revisit the SLURM script, when I use sbatch to submit this request, we have the nodes and tasks per node and so on that we saw before. This directive tells SLURM to submit my job to the debug partition. That's also sometimes called a queue. Anvil has separate queues for different kinds of jobs, which are listed in the Anvil user guide. GPU jobs, high mem jobs, AI jobs, and so on. The final 2 directives in my script ask SLURM to email me when it launches my program and when my program finishes. This lets me go and work on other things while I await my results. Exactly how long it takes will depend on how busy the system is. I could use the SQ command to check. We'll pause the recording and resume whenever my job finishes. So previously I ran SQ with -U, my username. If I repeat that command, I see that the queue is now empty. I did receive an email from Anvil indicating that my job is finished, so let's resume. If I do ls again, I see I now have 2 SLURM output files. So if I use cat to view the second one, but this time using 128 processing elements, found my same 81 solutions, but in under 3 seconds. So a significant speed up. By using SLURM to specify how many nodes and cores to use to run my MPI program, I can take advantage of Anvil's parallel capabilities and get my results more quickly than using my own computer. CircuitSat does not require any input values. The circuit it checks is hardwired into the program code. When a batch program needs input values, those are usually supplied using command line arguments. To illustrate, let's look at a different example. If I enter cd ... note that my prompt indicates I'm now in the examples folder. If I do ls again there, I see circuit sat where we just were, and genscan. The ... is Linux's abbreviation for the parent of a working directory. So cd ... took me from circuit sat back up to examples, and I can do from here cd down to genscan, my second example. My prompt changes again to indicate that I'm now in genscan. If I do ls there, we see files named 1x16-slurmscript.sh, feliscatus9.dna.plane, a program named genscan, and a slurm output file produced by sbatch. Let's use cat to view the slurm script. It looks similar to before. It says let's use one node, one task per node, that is one MPI process. This program is a hybrid of MPI and OpenMP, and I want to use 16 CPUs for that task. OpenMP lets me do multi-threading. At the bottom, though, I have commands. I copy an input file, feliscatus9.dna.plane, from my current folder into a scratch directory under my name. I export the number of threads I want. The slurm CPUs per task will be 16. And then I call MPI run, one process this time, genscan, anvil scratch, my folder, and feliscatus9.dna.plane, and CAT. The genscan program needs two inputs, the DNA file of an organism and a nucleotide sequence for which we want to scan within that file. Since we've already run genscan this way, we can use cat to view the slurm output file that it produced. Using 16 threads, it found 43,704,738 occurrences of the sequence CAT inside the cat genome. Since I was using 16 threads, it did it in under 8 seconds. This program takes over a minute on a normal laptop or desktop. So by using 16 threads to divide up the genome file and scan it in parallel, we get a big reduction in the total time. So now you know how many instances of CAT occur within the cat genome. If I must run my program interactively, I can request an interactive session from SLURM using the sinteractive command. I give it some arguments. -n is the number of nodes I want, which is 1. -n is the number of CPUs I want on that, or 16. I'm going to use the shared partition this time, just for some variety, and -a CDA080011, my allocation number. SLURM queues my request. And again, this depends on how busy the shared queue is. Oh, there it goes. We don't even have to pause. It's now configuring the node for us. And in just a second, there we are. So now note, I'm still in genscan, but my login node, login07, is now a247.anvil. I'm now on an actual computing node. So when my request is granted, my prompt changes to indicates where I am. There I can set up OpenMP by entering export OMP num threads equals 16. And then I can run genscan, MPI run -np1 /genscan /anvil /scratch /x -joel Adams Felis catus 9, DNA to plane, and then CAT. And we should see the program now running interactively. And again, it took about 8 seconds to find the same answer. The advantage of this is I can now look for other things. I could look for instance, tact. Our cat's very tactful. And again, under 10 seconds. And there were 8,550,841 occurrences of that. If I want to look at Catan, the Cats Play Settlers of Catan, there are only 2 occurrences of that. So the advantage of interactive mode this way is you can vary both your inputs. If I had a different genome organism available, I could vary that as well. When I'm done, I type Control-D or exit, either one. I relinquish my node back, and now you'll note I'm back on login 07 where I started on Anvil. The history command gives me a listing of all the commands I've entered. History, S-Interactive, the cat commands, etc., etc. When you use the up or down arrows to retrieve commands, it just looks in this history list and goes through it. Finally, I can type Control-D to end my login session on Anvil. That closes my connection, and now I'm back in the terminal application on my own computer. Congratulations, you've now seen how to connect to an Access resource using SSH. You can use Linux commands to navigate the system, and you can run programs using SLURM either in batch mode or interactively. Having seen all that, let's return to our presentation. To summarize what we've learned today, for security reasons, most Access RPs require you to set up SSH keys to use their resource. The Access Support Video Learning Center has an SSH for Access playlist on this topic. Your RP most likely has instructions for setting up SSH keys on their resource. Access resources use the Linux operating system, which you use your keyboard to enter commands on the command line. There are many Linux command line tutorials available on the web that can help you learn to use this interface. Since Access resources are shared by many users, most run programs using the SLURM job scheduler. In batch mode, SLURM queues your job until all the resources it requests are available. SLURM also provides an interactive mode for running programs interactively. For more information about using SLURM, see the Getting Started with SLURM playlist in our Video Learning Center. Using SLURM is just one way to interact with Access resources. Most RPs also support a browser-based interface called Open on Demand. It allows you to run applications that have graphical user interfaces, including MATLAB, RStudio, Jupyter Notebooks, and others. Support for Open on Demand differs from one RP to the next, so for more information about it, please consult with your RP. In the next presentation, we'll explore the Access support site and see different ways to get help when you get stuck. Thank you for watching this Access presentation.